Again, my name is Maximiliano A. Work at the numerical modeling and remote sensing department of the National Weather Service of Argentina. I'm also a PhD student at the Department of Atmospheric Sciences at the University of Buenos Aires. And I would like to talk about some results as part of doctoral research. Okay. In the process of data assimilation, it's of paramount importance to have a precise prediction of variance to represent the uncertainty of the forecast state. 3D vari is a classical assimilation technique that uses a fixed state-independent covariance estimated using climatological forecast information. And this approach is very, very cheap computationally, but we don't have a state-dependent covariance.
Massimiliano, I would suggest that you.
Yes.
I would suggest, because the bandwidth is not that good, I would suggest that you speak slowly and stay keep close to the mic and speak slowly, because the bandwidth is not very good, so that it's not so easy actually to understand you.
Okay. 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 And in the ensemble technique, the blue section, sigma, the covariance, is estimated as a sample covariance for the forecast ensemble. This provides us with a state-dependent estimate of the prediction error. Some important shortcomings in ensemble-based databases data assimilation are the subestimation of variances due to sampling error and the high computational cost. We propose to use a neural network to estimate the covariance data assimilation. In fact, we are going to feed the neural network with a forecast at the desired lead time and its initial condition. With this, the neural network estimates the error covariance. With this, we conduct a new assimilation cycle to generate a new analysis. Assimilation cycle. And we want to train this network without explicitly using information from the ensemble. Then we need to use a loss function that is sensitive to the forecast error. For example, one uses a loss function based on observation likelihood, assuming the Gaussian distribution, while Campo Real relies on the CRPAs and prior score. We are going to use a loss function based on a local error estimate in a kind of semi-supervised training in 3 different ways. Sorry, now it's clear? You hear me?
Yeah, we do, but it's it's not that easy. But so speak slowly as you try to do, which should be fine enough. Okay. Yeah, but so stay close to the mic and speak slowly.
Okay.
You could also try switching off your camera. So it's kind of set there not to, but that reduces the bandwidth.
Okay. Yes. No. Here. Here. It was. Sorry. We plan to conduct 3 different experiments, and I'm going to explain the difference between experiments. The main difference is how we train and the first one, we call it CORR for correlation. In the yellow section, shows the technique used to train the neural network, and the red section shows how to convert, if necessary, the output of the network to obtain the final covariance. Okay, to train the network for every sample in the training set, we calculate an online proxy of the error by comparing the forecast with the analysis. Here we compare forecast with the analysis. This is the proxy. And then we use this proxy to build up the loss function that effectively in the network. This is this equation, the loss function we use. Once the network is trained this way, it gives us an estimate of the standard deviation that will be with the climatological correlation, finally obtain the covariance matrix. This is here. So we in this experiment we estimate the standard deviation of the system, and using the climatological covariance, the climatological correlation matrix, we obtain the covariance. Okay. In the second approach, now, in the second approach, we are going to do the same, but in the PCI space. So the idea is we start by computing the ancient vector of the climatological covariance matrix. Then we calculate the error proxy, but now in the PCI space. And finally, we use the previous loss function to estimate the variance in PCI space. So the idea is the same as before, but in a transform space, in a space where the variability, the space is aligned with of the error. Once the network is trained, we need to transform back the variance from PCA to the state variables, the variable space, to obtain the covariance matrix. This is the last formula in the section. So we find the standard deviation vector in the PCI space, and then transform back to the variable space. The variable space. And the last experiment, in this approach, we use a local estimation of the covariance matrix. In this case, we use the outer product of the estimated forecast error as a proxy of the local error value. Here. So once the network is trained, we didn't have to do any transformation, because now the neural network gives us this local estimation of the covariance allowed us to train not a full covariance, but perhaps select the diagonals we want to train. So it allowed us to make some localization in the covariance. Okay. But what is very important about this slide is that we use the two-scale Lorentz 96 model to generate the true model, the true rank. Then we generate observation by adding noise to the state in the true set. And we use a one-scale Lorentz 96 model to generate forecast, simulating imperfect model. Then with the forecast, and the observation. We generate analysis using ensemble Kalman filter, and now with the analysis and the forecast, we generate the data set that will be used to train the neural. And also, it's important to note that the state of the system, the observation, is 50% of the state variables, meaning that there are state variables that are never observed, and that we use a multi-layer perceptron with two hidden layers. So the network is pretty simple. Okay, this is a summary of the experiment we conducted. As a reference baseline, we use the 3G bar and both two ensembles. One with 50 members and one with 5 members. And the experiment we explained before, the CORR is the one that learns the standard deviation on the state variable space. PCA learns the variance in the PCA space, and COV learns the covariance matrix. Okay. Well, what we are looking now are the covariance matrices estimated by each method. The first and second row are snapshots of the point estimate covariance for 2 consecutive times, while the third row is the mean over all the testing data. And the columns are the experiment. On the right of the figure here, it's shown the Frobenius distance from each method with a 50-member ensemble. So the idea is to compare the structure of the covariance matrix estimated by each method with the ensemble. For example, CORR and PCA do not seem to preserve much of the structure. Except for this point, this maximum, the rest of the covariance are pretty different. But for co-experiment, even though it estimates a band matrix and its 4 and 5 feet diagonal are fixed to 0, the structure of the 50-member ensemble is organized. You can see some pattern that is respected. Okay. Now let's see how these covariance evolve over time. Okay, this figure shows the time evolution over 100 cycles of assimilation of only one state variable. In this case, it's an observed variable. Remember that not all the variables are the figure on top shows the evolution of the variance for each experiment. The figure in the middle shows the value of the first covariance, and the figure on bottom, this one, the value of the second covariance. And on the right here are the correlation coefficient of each method with the 50-member ensemble. Something notable about the figure on top is how the PCA, which is the red line, shows very little variability as opposed to the correlation, the green one. And CORR seems to follow the ensemble pretty well, but PCA No. And also, this behavior is reversed in the plot in the middle, where the green line is pretty flat, and the red, the TCM, follow the ensemble much better in the first covariance. And if you see the correlation at the bottom of the screen, the core experiment is almost uncorrelated. So let's see what happened with the non-observed variable. It is interesting to distinguish between observed and observed variable because the assimilation method does not have observation to correct. And so the impact of estimated covariance in the resulting analysis is huge. And now here the results are remarkable how PCA performed in this case. Look at the amplitude of the variance compared to the observed variable. And it was almost flat. Now it has a great variability, and we could see that follow the ensemble too. And this makes sense because PCA networks then are uncertainty in a space aligned with the maximum error variability. So it managed to focus where the uncertainty is large. Okay. This is only the network that learned from the covariance directly. And what makes this experiment different from the other is that it has more degree of freedom to estimate the covariance, because estimate the covariance, not just the diagonal. And the performance of this method is notably better for both variances and covariance. It follows very close to the evolution of the 50-member ensemble. The correlations are almost 70% in all the estimated parameters. And the same happen, and the same is true for the observed variables. The network appears to capture a large part of the variability, variance and variance. And again, now the high correlation coefficient. But so far, we have made a qualitative analysis of the covariance obtained with this method. But we are interested in knowing the performance of each method in the long assimilation cycle. Here, the figure shows the total error reached by each method over 10,000 cycles of assimilation. And also, we have distinguished the error in the observed variables and in the lower. For me, the biggest surprise was PCA, because in the qualitative analysis, it was not doing very well. But I think this is because, again, PCA concentrates its predictive power where the error variability is higher due to the lack of observation. No? And in particular, this is where the assimilation method most needed. And again, the error of the covariance method is impressive. It managed to beat the small ensemble, this one, despite the small ensemble Kalman filter, and it's even competitive with the 50%. We can mention that we use neural network to estimate the uncertainty from a deterministic forecast. That we train network using the loss function based on local error estimation that achieve a prediction that allows long assimilation cycles, even improving the performance of the bar and a much lower cost than this time. And we believe that this is because network trained this way managed to capture an important part of the structure of the state-dependent error. Right, and finally, we lead us future work to analyze how this thing can be extended to high-dimensional problems, because we are estimating variance, perhaps the location variance will be necessary. Okay, and that's all. Sorry, I messed up with the computer.
Okay.
I hope you. Yes.
Okay, thank you, Massimiliano. So the problem is that I guess it was very difficult to hear you and to understand you. So we don't actually have any questions in the chat. Fortunately, also your slides were rather clear, but it was difficult to follow your explanation because it's most likely due to your mic, actually, because you are able to share your screen quite easily. So it is possible that your mic is the culprit. I may have a questions, but the thing is that I don't know whether you discussed that or not. There is this. So did you try to actually compute the root mean square error and vary the density of the observation? So you studied the case with the alpha observed case, and you looked at the sites that were observed or not. But did you try to vary the density of the observation? See how the root mean square error would actually change?
No, we made this experiment with 50% observed state because the Lorentz, we use only 8 variables, so we don't have much space to change the density. Perhaps because less observed variable is too few, and no, and the pattern of the observation pattern is also fixed. So the variables that are observed are always observed. The ones that are unobserved are less. And the density is fixed.
Okay, so why do you use only 8 variables for the 2-scale Lorentz model? I mean, so how about the cost of your procedure? I mean, is it? I mean, you alluded at that at the very end of your conclusion, but is there really a cost attached to? I don't see why it would be a major problem to actually scale the 2 Lorentz model up to the 30 or 40 variables of the model. So why choose only 8 variables?
Well, this is the preliminary experiment. We use a little Lorentz variable because it's easy to train, faster to train. The idea is to understand if networks are loss function and the techniques to train are able to capture the covariance matrix. If they can do it if they can't do it in a very small experiment, it's a problem. So problem to higher dimension.
Okay, okay, that's clear. Okay, so no questions, but I guess that's, I'm sure that a lot of people would have liked to ask questions, but it was quite difficult to follow. Thank you very much anyway, Massimiliano.